Hello, my name is Kuncheng. This is homework 10 problem 1 presentation for course probability and stochastic process. And for the first problem, it require me to introduce the definition and the simple property of the example of stochastic processes. And from lecture notes, and the first example is Poisson process. For this one, we discussed a lot previously, and we have the three simple property. The first one is the number n t1 t2 of the point n in the interval, the time interval, and of the length t equal to t2 minus t1 is a Poisson random variable with a parameter gamma t, and we have the function. And the second one is if the interval t1 t2 and t3 t4 are non-overlapping, then the random variable nt1 t2 and nt3 t4 are independent. And the third one is at the time moment t, there is no more than one Poisson point, and the x can shows the Poisson point. Using the point ti, we form the stochastic process xt. So this graph can be showed the Poisson process, and we have the property. So the first one is the first order probability masses function. It can be easy to get from here. And we have the mean function equal to delta t, and the autocorrelation, not delta, gamma square t, and plus gamma minimum t1 t2, because the t1 t2 we don't know which one is greater. And we have the autocurrence and equal to gamma square t1 t2 plus gamma minimum t1 t2 minus gamma t1 times gamma t2 and equal gamma minimum t1 t2. And discussion is easy, because the mean of the according to the function, the mean of the Poisson process is delta t, which is a linear function of the t, and we can easy to find it in our life. Like if longer time we wait for or do something, and maybe we have a larger number we can do or we can see, so it's easy. And for the second example is Poisson increment process is defined as yt equal to x xt plus, I don't know how to read, t plus we can theta, we assume this theta minus xt divide theta, where xt equal to where xt is Poisson process. And we have the function, the first order probability masses equal to exponential negative gamma theta, and gamma theta n squared divide n increment. And we have the mean e, the mean equal to the gamma, and we have the autocorrelation r t1 t2 equal to gamma square. So we have the two different conditions for this one. Gamma t square if the t1 minus t2 greater than the theta, and another one is another condition is t1 minus t2, the absolute value less than theta, and this is the function of the autocovariance. And for the discussion, this process is introduced to prepare us to define the Poisson impulse process. It is interesting to see that in the expression of the autocorrelation and this function and this condition is a triangle with the area gamma, which is independent of the theta. And let's see the third one. The third one is point impulse process is defined as a zt equal to derivative xt respect to the time where xt is Poisson process, and we can easily to see the graph and the response to this one, because this is derivative, and we have the mean zt equal to gamma, and we have the auto correlation equal to gamma square plus gamma theta. That's it, impulse function theta t1 minus t2, and autocovariance equal to gamma theta t1 minus t2. For the discussion, the process zt minus gamma has zero mean and autocorrelation equal to gamma theta t1 t2. This means the zt minus gamma is a white noise, and in the real world there is a short noise can be defined as the output of the linear time invariant system with an impulse response ht and input as a Poisson impulse process. And for the fourth example is a semi-random telegraph signal. This signal is defined based on Poisson points. Again, the number n t1 t2 of the point ti in the interval t1 t2 of length t equal to t2 minus t1 is a Poisson random variable with the parameter gamma t, and the xt can be defined equal to 1 when k is even in the interval, and xt equal to minus 1 the k is odd in the interval. And for property of this one, we do remember there is a problem for the previous homework. We do the proof for the semi-random signal. So the probability x equal to 1, we have the exponential negative gamma t times exponential gamma t plus exponential negative gamma t divide 2, and this one we just change the plus to the minus, and we have the mean equal to exponential negative 2 gamma t square, and the autocorrelation equal to this one, and the covariance equal to this one. And for the discussion, if t is not too high, the probability mass xt equal to 1 should be a little bit higher than the half. And if the t goes to infinity, and the probability mass would goes to the 1.5, and the mean goes to 0, and the correlation goes to 0 when t2 minus t1 goes to infinity. And if the t1 minus the t2 minus t1 goes to infinity, means xt1 and xt2 are less correlated. And for the fifth example is random telegraph signal. So this one is similar like the last one. So just give a constant coefficient before the xt, and we have the probability equal to 1.5, and where xt is semi-random telegraph signal, and we have the yt equal to 1, also equal to 1.5, and we have mean equal to 0, and we have this almost the same autocorrelation, and is different for the autocurrence. And this one can be make us guess. We can guess from the property, and we can guess the yt is the ss, means it's straight. Let me see. A straight sense stationary process by this property. And for the sixth one is random walk. For this one can be defined toss a fair coin n times. K is the number of the head in n tosses, and we have the function the xnt equal to ks minus n minus k times s equal to 2k minus n times s. And we have the probability method is probability equal xt equal to xnt equal to rs equal to this function, and we have the mean equal to 0. We have the autocorrelation equal to the minimum n and m times s squared, and also we have the same autocurrence. From the probability mass, we also can guess when n goes to infinity. For this one, we will have the Gaussian density for this situation, and the autocorrelation function contains a term minimum t1, t2, which come from the property of the independent increment. So for the last example is Wiener process. The we can write to the wt, and we have the situation is t goes to 0, and s squared divided t goes to alpha, and n goes to infinite equal to limit xt, where xt is the random walk. And also we have the function for this one is density, the first order density function, and we have the mean equal to 0. We have the autocorrelation equal to minimum t1 t2 times alpha, and we have the autocurrence equal to minimum t1 t2 times alpha. And for this one discussion, we goes to a website to get some property from the website. The first one is W0 equal to 0, and another one is W has an independent increment. The third one is W have a Gaussian increment, and W has continuous pace. The property R belong to the Wiener process, and the W means Wt. That's for the first problem. Thanks.